Okay, so let's get officially started now. A couple of announcements before I forget. There is a end of course student survey going around. Feel free to be honest on it. The TAs are supposed to be handling it. I don't know if they've passed it out yet, but they probably will before the course is over. Today, I mean, before today's class meeting is over. And it's confidential, which means I don't read it. And in fact, they never even show me the results anyway, even at the end of it, which is kind of weird because I could probably use some feedback. So feel free to answer honestly. Tell what you liked about the class, about the school, stuff like that. I have no idea what the questions are, but it's not going to affect your grade or anything of that nature. It's just something where the school can get some feedback to figure out how they should change things in the future. The second item is the ITU Cares Japanese Relief Fund thing. I don't see the little Tupperware dish or the thing for it, but we're supposed to have some sort of a jar or something. So I'm not quite sure what happened with that. But the TA is absent. Oh, that helps. Okay, so all right, so forget about that. But that contribution, and 100% of the funds are going to Japan. So let's see. And another announcement is that next week we have it's twofold. Next week we have final exam review, and we also have a WASC visit. And I hear through the grapevine that the WASC people are actually going to come into this class, perhaps. Which means if we have a lot of people, it'll be great. But it's twofold. You want to show up anyway, because I'm going to be reviewing everything that's going to be on the final exam. And so it's your best opportunity to figure out how you're supposed to study for it. Because we've covered a lot of topics in this class, and you're going to want to narrow something down in terms of your studying to make things manageable. And so I'll be going over that next week, and also you'll have an opportunity to visit, I believe it's Tuesday, Wednesday, and Thursday. The WASC teams are visiting with students, so find out when your student meeting is. You can go and talk to them and participate in the student involvement. They're also going to be coming in and looking at classes and stuff like that, and they'll be talking to the faculty and the administration and stuff. It's kind of our checkup or whatever. If we score well on that, if we look good, then we'll get our preliminary accreditation, which is what we all want. So it's to your benefit to participate if you can. But I have no idea. You find out from the TA what the schedule. I don't know. Not really quite sure the schedule. The only thing that I've heard is that we might have some WASP people sitting in on the class, which would be exciting. It would be fun. So hopefully we'll get a good turnout. Show a lot of students, but you'll turn out anyway because you want to know what's on the final exam. So. The final exam week is a 2-week period. If you haven't been around and you don't know about this yet, the schedule's already posted. If you don't like the time that you've been assigned, you can suggest another time. You send me an email message, and I tell you you tell me which group you want to go in, and I move your name into the other group. So you can take it at whatever time you want. You can take it actually on a weekend day. We have 2 weekends, the 16th, the 17th, the 30th, and the 1st that are available as well. Or you could take it during one of the other classes as well. So today we're going to go over lecture 12A, which is going to be on the architectural design to finish that up. And we're also going to, next week, we have one more lecture we're going to hit. So I'll do the final exam review towards the end of that next week's class because I know some of you don't show up until halfway in the middle of the class, and I don't want to repeat myself. So we'll go over reusable objects, which is actually kind of interesting, especially if you're taking the object-oriented design course. But that's more object-oriented design stuff. Today I want to talk about more generic system architecture information to complete that concept. And I was also informed that I didn't go over assignment number 5, so I want to go over that one as well, give you the expectations and stuff on that. So any questions before I get started? Anything about final exam week or anything? Okay, good. So assignment number 5 is develop a test plan. And hopefully you do this one after you do the architectural design. Because the architectural design is assignment number 4. And that one is about the mine pump control system. And after you've read that one and you've done the architectural design, you should probably know that system inside and out at that point. And you can base your test plan off of your architectural design, which means some of you might come out with different designs, different systems. So you want to definitely do assignment number 4 first. And what you're going to do is determine the preliminary tasks for your test plan. And you're going to develop the actual, and then you're going to actually develop the test plan, which should be particularly based on the criteria and risk assessment. So you're going to complete the following tasks to develop your test plan. And if you go on the internet and you Google on test plan, you're going to see 200-page documents. You're going to see, or 20-page documents, lots of stuff, and you'll see formal test plans. Here, take test plan with a grain of salt. Maybe take the word plan out and call it test summary. You're not coming up with an official. In fact, I didn't actually cover the writing of an official test plan because that's going to vary depending upon what company you're working for and what you're actually doing in terms of the format and the style. So scratch that stuff off the list. Go back to some of the testing stuff that we talked about. I talked about a couple weeks ago. We had almost about three lectures or so, 2.5, 3 lectures on testing. Talked about unit testing, talked about system testing, talked about all sorts of different types of testing. And I think I also directed, if it was this class or the weekend class, I'm not sure which one of the classes I did this for, but I also pointed out in the Software Engineering 1 notes that are available on bhacker.com, there's a thing on testing inside of this SE Notes download. It's about, it's a Word document, it's about 60 pages or so. There's a whole thing on testing in there as well. So you can use the lecture notes, and you can also use that document from the first class if you didn't take Software Engineering 1. That will go through essentially what the different types of tests are. However, there's no requirement that you use anything that was introduced in terms of the different types of testing. And the requirements are that you complete the following tasks. And here's what you're going to do. You're focusing on risk assessment. Because what you don't want to do is have a non-working program or non-working pump controller. So you're going to identify the focus areas to be covered by the testing. You're going to identify the resources that can be used during this testing. And you're going to assign appropriate personnel, you have to make these people up, to develop a test strategy and test schedule. So after you complete these tasks, you're going to complete the next ones, which is going to be to develop the test strategy, the plan, and the timeline. Make up the timeline. This is a fantasy project. In fact, I don't think this project actually even exists. I mean, I don't. Well, maybe they do have pump controllers. I'm pretty sure they do. They pump water out of mines all the time, I'm sure. But this is something that's totally fictional. And so make up the people, make up the timeline, make up all of the information. You're going through a scenario. And when you develop the test strategy, and the plan, think informal. I don't want a formal plan out of this. You could write it up sort of like an outline if you want. You could write it into a form of an essay. You can write it in bullet points. You can outline it any way you want, any format you want. You don't have to use a traditional test plan format. So some of the resources that you might need are hardware, software, labor, tools, licenses maybe. I don't know. You may not need all of these. Location. You might not need any of these resources. Probably going to need hardware and software and labor. Yeah. So verify that you've taken into consideration the physical planning and installation requirements of the pump controller that you're putting in. Review the plan thoroughly before submitting it. Use the review to focus on the timeline, the requirements, the costs, the steps necessary to complete your plan. So what you're doing is kind of vague. And it's left to your own interpretation. And so you have academic freedom to interpret this any way you want. You can come up with your own style. If you've actually done a test plan before, if you've actually done a test plan before, you can use that format. You can use any unique format you might want to come up with yourself. You can go on the internet, look up test plan. Concept being is it's not graded on the format. I don't care about it. What I want you to know is, what I want to figure out is, can you focus on different testing strategies? And it's about your testing strategy. So as an example, you're going to have to do some system testing. And you're probably going to have to do some unit testing. You probably want to do some acceptance testing. And if you go through the lecture on testing, there's 2 or 3 of them, you'll find out all the different examples. You don't have to get into a lot of detail. You're basing it upon your architectural design that you've come up with, and you're going to focus on the areas that should be tested. in your design, and it's all dependent upon what you've put into your design. So if something's not in your design, you don't have to test for it, obviously. If you did put something in your design, I would expect you to come up with a test for it of some nature. Use a variety of different tests and figure out, well, if you were actually going to try and test this, how would I do it, kind of thing. And then you'll end up understanding or realizing how complex this really is. It's actually, to have you put together a test plan for this would probably be like a 3-month project, probably, is what I'm thinking. I mean, if you were really going to do it. So I'm not expecting a real plan, long story short. Questions about the assignment? Expectations on it? No? You can get everything you need out of the lecture notes, actually, out of the lecture I did. You don't have to worry about security either, or reliability or dependability or any of those other things. But if you want to add it in there, you can. If you want to put in some tests for security, make sure no one breaks into the mine shaft or something that steals your pumps. Or safety, maybe. Safety requirements, you could test for some of those. But focus on risk assessment in terms of if something were to go wrong, what should we test for? I mean, obviously we don't want the whole mine shaft flooded out. We don't want the water to be put in some residential house or something. We don't want to make sure that thing doesn't blow up or something. That might be a problem, or catches on fire or something. So think about, in this particular environment, what are some of the things that should be tested for? What are some of the problems that might happen? And if you don't know anything about mine shafts, make it up. Make up the people, make up the resources, make up the money. You're not even given a budget. How do you even know what you're supposed to spend on this? So make it up. So you set the stage for it. So it's an exercise to get you to start thinking about what goes into a test plan. What are some of the things that you should be thinking about? And even the exercise of making the stuff up is actually kind of educational, because now you're thinking, oh, money. Yeah, it does cost something. What does it cost? I don't know. Let's allocate some funds to this. And you start looking at it going, I wonder if that's realistic or not. And it doesn't have to be realistic. So, any more questions about assignment number 5? It's actually, I want to say, it's probably the easiest assignment of all.
The hardest one.
You think it's the hardest one of all?
Yeah, fourth also. Fourth and fifth.
Well, they are the later assignments. Yeah. The fourth one's hard. It's not going to be hard after today. I don't know. Have you guys? Has anyone done the 4th assignment yet? That person is locked out, by the way. Or they're not really locked out. I think that the door handle is kind of heavy. That door is heavy. People are mistakenly locked out when they're really not. So. All right, this is lecture 12A. And actually, you know what? Before I start, because I totally forgot to do this earlier, let me tell you which lectures are optional so you can write those down, because some people are actually starting to study early. I'm going over 12A today. 12B, just write this stuff down if you want, is optional. I'll give you this information next week, but right now you can scratch these things off your list. Lecture number 13, 14, 15, 16, and 17 are all optional. These go into different, 14, 15, 16, and 17 go into different types of software engineering methodologies, like agile software development, service-oriented software. Well, actually, I could bring them all up, but it would be a waste. You might find some special topics in our distributed computing. I think 12B is distributed architectures, actually, or something of that nature. Nope, software engineering, architecture, design. I would look through them to see if any of the topics are of interest to you. But it's not testable material that you're going to find on the final exam, because I'm stopping the final exam with lecture 12A. So it'll cover 11, that we're going to cover next week, and 12A that we're covering today. But I'm not going to cover the rest of them. And I purposely kind of put the miscellaneous stuff at the end, just for that reason alone, because I wasn't quite sure how far we were going to get through it. So, but I will repeat that again next week. But just in the meantime, for those of you who are preparing ahead of time, you can scratch those off your list. All right, 12B. 12B. All right, so last week I talked about object-oriented architectures. Actually, the focus was object-oriented design. starting with an architectural approach, working down to objects, taking those objects and looking at the interfaces and the control, and basically presenting it from an object-oriented analysis and design perspective. This lecture is more generic. This is focusing solely on the architectural design. And what I want to do is give you some different models. You don't have to follow any of these models for the fourth assignment. You can do your own. You can do it in an object-oriented fashion. It might be easier for you. But if you don't want to take that route, here's some more choices that you can do. And this also will help you kind of maybe put the pieces together to understand what we were talking about last week as well. So establishing the overall structure of the software system in terms of the design, what we're looking at is the system structuring, which is the architecture, and the control models, modular decomposition, domain-specific architectures. When I say domain-specific, that would be like client-server, peer-to-peer, different domain areas of development lend themselves to different architectural designs, and we can represent that in terms of models. So the concept itself and what you should be thinking about in assignment number 4 is identifying the subsystems making up the system in terms of the framework. And that is actually what's referred to as the architectural design. It's the system itself that's broken out, decomposed into the smaller components, and those smaller components are somehow working together, which is why you draw lines between them usually. I showed you an object diagram before. Usually you have to actually think about the systems as objects or entities or something. You have to put a label on them. It's easier to call them objects, I think, than anything else, because especially if you're familiar with object orientation, it lends itself better in terms of the concept or the abstraction. So the output of this design process is the description of the architecture. So the software architecture is what we're looking at talking about. Architectural design is the first thing that happens, as I mentioned last week. We usually start out with that. That's that object diagram if we're doing a UML approach. It represents, can someone please open up that, oh, there, she's got it. There we go. And it represents the link between the specification and the design process. And it's carried out in parallel with some of the other activities. So right in the beginning, when you're doing your requirement specification and you're doing your analysis, normally you would have to have the requirements completed before you start on this. But when you start in with your analysis, before you actually complete your design, you're hitting architectural overview, architectural explanation right there at the beginning. And you can also work on other things at the same time. Once you know there's a database, the database architect can be figuring that stuff out, because none of that information goes into the architectural design. It's all afterwards. But you want to make sure the architectural design matches the design that's implemented. So sometimes they do them in parallel. Sometimes the architectural design kind of exists and then it gets polished up at the end, because we added this controller, we added that controller. When you're not following an object-oriented methodology, that's normally the case, because you don't know. Most of the object-oriented analysis that precedes the object-oriented design goes through all of the scoping of the system, goes through all of the control mechanisms and the relationships between the objects. So by the time you build the design from the analysis, you're done. And which is why object orientation is actually kind of easy in terms of this particular concept. In other methodologies, you don't necessarily have all the information you need until you have half the system built. And you can go back and fix the architectural design later so it matches. And it's more of a learning process, I would say. But usually this is done in parallel, or can be done in parallel. It involves identifying the major system components, its subparts, and how they're communicating with each other. And in terms of the design process, we're looking at the system structuring, and I keep calling it a control mechanism, but it's a control modeling the control of the system, and the modular decomposition. You have all of this in your air pump, in your water pump, or your mine pump, or whatever you call it. The thing that you're not going to get in the description is this right here. You're going to get the system. You're probably going to get the modular information, but the control is something you're going to have to make up. It doesn't exist in the description. It will exist, and it has to exist in your program. So what are these components? The system structuring, the system is decomposed into several different subsystems. That's usually easy to see. We have the main system and we break it out, how are we going to put this together? The control is the control relationship between the different parts of the system and how you establish that. That's the pump controller, or the switch box, or the router, or the component that's taking all of the other pieces and gluing them together to make them all work in terms of the system, in terms of the processing. This is what you have to make up. It's not normally in the description. So that when someone describes a pump to you, they're not going to say, oh yeah, and is that the attendance going around? There's so many distractions in this room. The description is not going to tell you that there's a controller, is what I'm saying. In terms of the modular decomposition, that's nothing more than stamping a label on the subparts. The interesting thing, though, is that the modules don't have to match the subparts or the subsystems. You might actually have a different set of modules that might encompass many subsystems. As an example, you might have 3 different parts that are part of this module, 3 different units, pieces. You can diagram them out in these 3 ways. You can do a system, a control, or a modular diagram, and they all would classify as an architectural diagram because that's the architectural process, is you're identifying those components. So the subsystem is the system in its own right, its own operations, its independent services that's provided by other systems. So it works together in terms, and is not normally considered a separate system. So a pump in the mine pump application program isn't going to work on its own. It's a subsystem component. In terms of the architectural model, this is a static, non-moving model that shows the major subsystem parts. The dynamic process modeling might also show process structures of the system. You could model this in a dynamic fashion and a static fashion. You can use all sorts of different tools and representations. You can also video it. You can actually show an architectural design in some sort of an animated fashion as well. Relationship models are such that the data flow is like a data flow model showing the relationships between the entities. We have different, and so this is the modeling styles that can be performed in terms of an overview. And this is generic. It's not object orientation. It's traditional style modeling. So in traditional style modeling, we had data flow diagrams, entity relationship diagrams, well, we don't have really sequence, but we could do flow charts, flow type diagrams, which is what this is representing. Interface, this one interfaces with that one type of thing. In terms of the styles, the architectural model of the system may conform to a generic model or style. It might conform to some standardization, which is what some of the standardizing companies are actually doing for you. So they're giving you templates of the models that should be created for the architectural design. So let's say you're following a Department of Defense strategy in terms of, system development methodology. You're going to have to follow through certain documentation to document the architectural design, to document the subsystems. And it'll have a best practices general format that you're supposed to follow with a particular style. The style you use for assignment number 4 is your own style. You can use anything you want. I've given you the object-oriented object diagram kind of style notation, but you can use anything you want. So in awareness of these styles, I can simplify the problem by defining system architectures themselves. However, most large systems are heterogeneous and do not follow a single architectural style, which is the catch-22 on the whole concept. If we could standardize it, we could come up with, this is how you model it. Other engineering disciplines, you can do that. Houses always have the same kinds of subsystems. There's heating, lighting, there's water, there's all sorts of different subsystems that you can model in terms of the diagramming. And you have certain floor plan layouts. You actually have a floor plan. You actually have this. In software, it might be, the architecture might be a client server or peer-to-peer. It might not have anything at all. It might be a standalone system. It doesn't lend itself well to standardization. So big projects, you're not ever going to end up with a standard kind of diagram style or format. In terms of the attributes, these are some of the things to think about in terms of descriptions that you're representing. Performance, localized operations to minimize subsystem communication. These are pieces of the architect that you're putting in. pieces of the architecture you're defining in terms of these control attributes. Security. You might use layered architectures. We saw a layered architecture last week with critical assets and inner layers. Safety, isolating safety critical components. Availability, maintainability. These are some characteristics or attributes that you could apply in the architectural design. And then in software, we have this interesting concept of the repository, which we don't have in building a house. There's no repository when you build a house. Well, unless it's a garbage dump or something, I don't know. Well, we have exchanging information and we have data flow. So this usually ends up being the database. So sometimes it's represented as a database. Sometimes actually it's just not. Sometimes it's represented as a repository because in the architectural design, we don't want to say we have a database. Especially if the design, we're doing this first, we haven't designed the system yet. We might not know that we have a database. We might not use a database. We might use a file or something else.
Which type of model we are going to follow during the architectural stage?
Anything for the assignment, you mean?
No,
Say the first part one more.
When you're architecture, when you're doing some programming,
yeah,
you need to know what type of programming model is going to be followed when you're developing the software.
Not at the architectural design stage. You really don't need to know what methodology you're going to use for the development, whether it's going to be object-oriented or whether it's going to be something else. You don't actually have to know that when you're doing the architectural design because you're not focused on the implementation or the design. What you're trying to do is just describe the system. In fact, that's a good point. Architectural designs don't have anything to do with the actual implementation or any of the details associated with the programming language or the environment, or the programming environment. All you're modeling is the finished system. You're looking to a mirror ball and you're describing what you're building in terms of its higher level components. So you might, yeah?
The next step is a requirement document or the specification document.
Yep.
It's been done using the repository, using the architecture.
Definitely. In fact, the requirement specification normally comes first. And then this comes as a second preliminary part of the analysis before the design happens. You build the design off the architectural diagram. Architectural diagram is a visual representation of the requirement specification. But it's showing you not the inner details, it's showing you the outer system components. If I were to make an architectural diagram of an accounting program, and I always use that because that's the only thing I know about. Just kidding. I would have accounts receivable, accounts payable, reporting, taxes, general ledger information. I have all these pieces that would be associated with accounting, and I'd draw little boxes and I'd connect them all. That would be my architectural design. If I were to do an architectural diagram of the ITU campus, I'd do a first floor, I'd do a layering actually. I'd do a first floor, I would do a second floor breakout, and then on the first floor, I don't know, I could probably put, classroom, seminar hall, and basically I'm just pointing out the subsystems or the subcomponents that make up this big picture. And in fact, I could probably just do it like a map and draw it out, and this is next to this is next to this, basketball court, bathroom, and then further on, just diagram it out. All you're doing is explaining in a picture. Can we please keep it down in the back? There's a lot of chatter. All I'm doing is explaining in a picture the requirements as visualized in a finished system, which just hasn't even been built yet. Which is why, originally I started out saying, sometimes we have to go back and fix the architectural design. Once we understand more about the system, we go, oh, this is a client-server model. We didn't know that. Oh, now we have to make it into a client-server diagram.
But during the development of the software, the client is asking this thing has to be inserted. Some of the product some of the element has to be inserted.
Yeah.
You cannot do it in one model. So you have to follow some kind of
Oh,
model.
you have many different models you're following. This is just one. This is just the starting point.
Like,
Yeah.
when you are developing a software,
Yeah.
you have to be very specific what kind of model you are following.
Yes. That's why I originally showed you the object-oriented model, because that lends itself better to an object-oriented design. And it actually lends itself better in terms of translation into, and we're going to see another representation of the object-oriented model. basically it's basically a representation of a standard traditional style of modeling, but it lends itself better to the development language and the environment for which you're going to actually build the system. Because if you speak the same language in the architectural design as you do in the implementation, you get better translation if you're in the same language or in the same methodology, which is a valid point, but unfortunately sometimes you don't know what you're going to use. If you don't know what you're going to use, then you go with a more generic approach. But you can actually do an object model on something that's not going to be implemented in an object-oriented fashion, which is why it's very popular. And most of the models you see out are now object-oriented type of models. They're object diagrams is what they are. And, you know, they slap the architectural diagram label on it, and they go, oh, it's an object diagram, but it's architectural design. Okay, let's talk about the repository for a second. So it's holding the data, and we can define data components. We could actually include this if we have a heavy-duty data collection and data exchange model that we're working with. And we would actually use what is referred to as a repository model that shows us data stores, and this is the data flow diagram actually, that shows us data stores, data inputs, data outputs, shared data that's held in terms of the centralized database and the repository. So when large amounts of data are being shared, the repository model sharing is most commonly used. And here's a kind of an example of a case toolset architecture that shows a repository. So we have in the center of the screen we have the project repository, and we have code generator, design editor that leads into and comes out of this repository along with some. Don't worry about these components at this point, but this is for a case tool set. So this is, if you were designing your own case tool, this is what essentially the components would consist of. You know, design, analyze, report generator, stuff like that would come out of it. So that's an architectural diagram, actually. It's using a repository tool set, a repository model as a tool set. So what are some advantages and disadvantages of this type of modeling in terms of its approach? The advantage is it's an efficient way to share large amounts of data. Subsystems need not be concerned about how the data is actually produced, centralized management, backups, recovery, stuff like that. You know, it takes away, makes it very simple. Sharing models published as a repository scheme. So you could take this essentially and implement it as the database, as the scheme. Some of the disadvantages: subsystems must agree on the repository data model. Inevitably, a compromise is going to be made in terms of not having to store duplicate information. You might have to change the format of something, a string or a character that turns into something else, perhaps, depending upon how the information is going to be shared. And data evolution is difficult and expensive, no scope for specific management policies, and it's difficult to distribute efficiently because it's hard to come out with a good distribution policy for this. Everything's going in and out of a centralized location, centralized point. Client-server architecture. When I say client-server, everyone goes, oh yeah, I know about that one. Because I teach it to you, they give you the architectural design. You see it day number 1 in a client-server class. When they're teaching you networking, they're showing you the architectural diagram right there. So most of you have seen this already. Could you please keep the chatter down? I feel like I have to yell over you. Thank you. Oh, now it got quiet. Good. Good deal. That's how it should be. All right. Distributed system model, as a definition, it shows the data the processing is distributed across a range of components. So client-server we always think of as a network kind of thing. It can actually be a program design that we're modeling. So we have a set of standalone servers which provide specific services such as printing management. We have a set of clients that are connecting to the servers. They're called clients. In terms of the network, it allows the clients to access the servers. Here we go. Here's a film and picture library where we have catalog server, video server, picture server, hypertext server, all these different servers that have different functionality that are associated with them. Client 1, Client 2, Client 3, Client 4. Normally we don't see so many bubbles for the clients. You could draw this. If you have more than one client, you could say clients, make it plural, put one bubble up there connecting. This is for illustration purposes to show you we have tons of clients and they're going through this wide bandwidth network. Sometimes we don't even see that. Sometimes we just see the clients connecting to the servers, assuming that there's a network in there. So it depends on how you want to draw it. But if we were trying a diagram for the film and picture library system that was working in a client-server type of architecture, that's pretty much what it's going to look like, with some variations on personal things. And that's why, essentially, we see that all the time when we take any networking class. You're going to see network diagrams. In fact, if you go into Visio as a tool set, you'll see model tools that'll say client-server, distributed, peer-to-peer. And you pick one of them, and it gives you the symbol sets, and you can just drag and drop things on a canvas, and it assumes you have a client, it assumes there's a server at some point. So, all right, advantages. Distribution of the data is straightforward. It's pretty easy to see the lines of communication going on here and how the data is working. This is not a repository model. So keep in mind this repository model is all going into a central point, and it's demonstrated by different functionality. Here we have a straight line coming through a client through this network into the server. So it's really just a client-server connection. So the distribution today is straightforward. It makes effective use of the network system. It's a network protocol. It's a network diagram. It may require cheaper hardware. Easy to add new servers and upgrade existing servers in terms of the architecture if we were using it in the real world. Disadvantages. No shared data model, so subsystems are used for data organizations. Each one of these guys down here are doing their own data organization. In fact, they probably have their own database, each one of them, which is not very efficient when you think about it. Redundant management in each server. Basically the same problem with the databases. You've got duplicate work. No central register of the names and the services. May be hard to find out what server services are available because there's nothing keeping these guys together in terms of the model. So we have no controller. We could implement it right here if we wanted to. We would actually put a middleware in there. We would connect it to an RMI or something, or we could add to it would change the nature of this particular model. We'd take it away from a client server and actually put it into something else. Abstract machine model. This is sounding like a pump. Used to model the interfaces of subsystems. Organizes the system into a set of layers or abstract machines, each of which provide a set of services. Sounds like a pump from a mine shaft. Supports the incremental development of subsystems in different layers. And when the layer interfaces changes, only the adjacent layer is affected. However, often difficult to structure systems in this way. Here's a version management system, version control management system, that's in layers. So this is actually kind of difficult to look at in terms of the abstract concept. How come, it got quiet and then it got loud again? Did we have a problem back there? Oh, power? Oh, okay. That's what happened. All right, so the version management system architecture. We're looking at the operating system, the database system, the object management, the version management system that's running on top of it. They are actually interrelated components that are running essentially inside of each other, which is why this diagram looks like this. They're not spread out all over the place. You could spread it out. You could create different layers if you wanted to. This is what's represented by the layering approach. One is on top of the other. You may not get that in the water pump. You're probably not going to get that in the water pump. But what you're looking at is abstraction. You're looking at a controller abstraction, a pump abstraction. It represents the concept of what's being performed. Control models. So these would be like, now we have music next door. I'm beginning to really hate this building. Anyway. All right, control models. I'll keep my personal information away. They're concerned with the control flow between subsystems. So you could add a controller, let's say, to the abstract model. You can mix and match, which is what you're going to end up having to do, which is what in the real world people do. They have a repository, maybe. They have a client server, maybe. They have some control mechanism going on, maybe. They have an abstract model they're working with, maybe. So what you're doing is you're combining these different techniques, depending upon what's appropriate, what's being applied. So in terms of the control, we have distinction from the system decomposition model. It might be centralized, it might be event-based control. So I would think for a mine shaft pump controller, it would probably be more event-based. If there's water, we need to use it. If there's no water, we don't need to use it. Depending upon the water, each one of the subsystems can respond externally to externally generated events from other subsystems from its system environment. So if the bucket's full, if the pump's working, you need to turn it on. If the pump's not working, you need to turn it on. If the bucket's full, you need to empty the bucket, whatever mechanism you're using for whatever control. In a centralized control, one subsystem has overall responsibility for the control to start and stop the other ones. So one can start and stop, or each one of the controls, each one of the mechanisms can actually be independently operated. Obviously, there's a lot of flexibility in the way you would design the system, either event-driven or not. In a centralized control system, to give you some more specific examples, the control subsystem takes responsibility for managing the execution of all the other subsystems. This would be like an elevator controller. So you press a button, and you're pressing a button on the main control panel, and it says, I want floor number 5. Well, it's going to go to floor 1, 2, 3, before it gets to 5. If it finds other ones, it's going to stop, and it's going to stop, if someone has pressed number 1, let's say it'll stop on 1. Then it'll stop. Or it will control the movement of the elevator depending upon the algorithm that it's been told to use. Where you have a centralized control. So you have a call and return model, or you might have a manager model. And the call and return is a top-down subroutine model. It controls the start at the top of the subroutine hierarchy and moves downward. So it's going through a sequence of systems and sequence of events or controls or commands. The manager model is concurrent, so it's managing simultaneous, perhaps, different events. One system component controls the stopping and the starting, coordinating of the system processes. Can be implemented in a sequential fashion as well, with using case statements. It's all implementation dependent. The model is independent, implementation independent. In fact, all of the architectural designs that you're coming up with are independent of the implementation. This is just the model of what it is you're trying to express. Here we go. The call and return main program here has routine 1, routine 2, routine 3, and it's going through a hierarchy of events. You could model it like this. You could create, this is an architectural model of a control, call and return model of a centralized control system, in which you've diagrammed out all of the sequence of activities that can flow from a particular event from the main program. Here's a real-time system control. And this is where you're going to get system controls. You might have a real-time, if you wanted to implement it in a real-time fashion, you could actually spec it out as a real-time mine pump, water controller system, whatever. Where you have sensor processors, actuator processors, computation processors, user interface, fault handlers, all that are controlled by a system controller in the middle. And the system controller is responding to events that might occur. So it's more event-driven. Or it's also actually centralized management of the control. But that is another example of an architectural model, actually. These are all architectural models that I'm showing you. In the event-driven system, by contrast, just like event-driven programming, it's a response that occurs given some particular event that might happen. So it's driven by externally generated events. Timing of the event is without the control of the subsystem, which might actually process the event. Two principal event-driven models are the broadcast models and the interrupt-driven models. And this is getting into way too much detail, however. If you know Linux, Unix, you're familiar with these and it's the same kind of event-driven process that interrupts play in terms of the operating system design, where we can broadcast out to everybody, hey, I need someone to print this job, or we could send up an interrupt and say, hey, print this job now, kind of thing. So it's a form of communication. It assumes you actually have some sort of a background in event-driven kind of behavior. Other event-driven models include spreadsheets and production systems, actually. So, the broadcast model by example, effective in integrating subsystems on different computers or networks. It's like sending out a message. Well, going back to the Unix example, we broadcast, we're shutting down now. 5 minutes, close all your programs, because the server is going to come down, or something's going to come down. It'll broadcast out a message to everybody so that they're aware of the situation. And it's a subsystem control from another subsystem, or from a control system. And the control policy is not embedded in the event or the message handler. It's a separate kind of control policy. You don't have to know when or where the event's going to be handled or why. It's just broadcast things out. Here's a selective broadcasting model where we have an event and a message handler in the middle, and we have subsystem 1, 2, 3, 4, and everybody's getting the same message. We broadcast it out. So they used to call it the bullhorn effect. You know, when you, now they call it spam mail. Through the generations, definitely the terminology and the acronyms have changed, but broadcasts, I always think of spam mail when I think of broadcast now. Massive email blasts, send me garbage. Interrupt-driven systems uses real-time systems, fast response to events, and usually hardware generated, usually some system that sends up a signal that's being caught and interpreted. There's an interrupt table. It looks up and says, oh, the CD-ROM drive is open. Oh, the CD-ROM drive is closed. And you process the event given the signal. So you have a known interrupt type, which is there's a handler defined for each one of the types. Each type is associated with a memory location, where the hardware switch causes some sort of transfer to the handler to take over. Allows for fast response, but complex to program and difficult to validate, because you can't go back and check who sent the signal. Where did this interrupt come from? And if you don't catch it, you lost it. And if you haven't handled it correctly, you've lost it. And here's an architectural diagram of an interrupt-driven control system, where we have interrupts coming out of here, an interrupt vector, like some sort of a table that's being stored. Handler 1, 2, 3, 4, process 1, 2, 3, 4. And this is actually kind of a Linux-looking diagram of how interrupts are actually handled. Over here we have the abstraction of the operating system, actually. And in fact, the operating system would be blanketed on top of all that stuff, actually. And in processes could be some program that runs to handle each one of the interrupts. Modular decomposition. This is the best, easiest, save it for last, way of architecturally diagramming. We don't know, let's say we don't know the architecture. Let's say we don't know anything about the client server. We don't know anything, whether it's going to have a controller or not. We could take the system and think of it in terms of modules and do a module decomposition on the system and diagram it out in an architectural diagram, which is all this is doing. So it's another structural level where subsystems are decomposed into modules. This is the traditional style. However, what's a module? You know, you might as well just take it a step further and create an object diagram out of it. You know, and we have to take the system. If we're going to do an object-oriented design, we're going to have to basically define objects anyway. But before object orientation, we had modules. And they were procedures, functions, programs, subunits, subsystems. Modules are everything. And then we say, well, in architectural diagramming, we move it up a couple, 200 feet. And we say module, that's the accounts receivable module. That's the accounts payable module. That's the reporting module of an accounting system. That's the tax module, the refund module, or something, whatever. All right, so 2 module decomposition models are covered. The object model, we saw that last week, where the system is decomposed into interacting objects. That was the purpose of last week's lecture. This week, to add on to it, we have the data flow model. We've seen that already. Oh, actually, we may not have seen it in this class. You saw it in Software Engineering 1, if you took that course, where the system is decomposed into functional modules, where it's transformed into inputs and outputs. If you remember the data flow diagram, we had input, processing, output, and these processing buttons, bubbles, were the data. And we watched the data as it flowed through the system, or the data flow diagram. All right, also known as a pipeline model as well. In other engineering disciplines, it's more often called pipeline versus data. Software people call it data. If possible, decisions about concurrency should be delayed until the models are implemented. So object models, this should look familiar. The structure of the system is set in loosely coupled objects through well-defined interfaces. So we have the objects and we have the interfaces between the objects. The object decomposition is concerned with identifying object classes, their attributes, and operations. We talked about that last week. When implemented, objects are created from these classes, and some of the control models are used to coordinate other operations. So that's what I mentioned before. When we read the description of the problem, when we lay out all of our objects, then we invent control mechanisms. We have to actually add that because it's not in our description. And that's the tricky part. And I shouldn't say it's really tricky. That's the interesting part. Here's an invoice processing system. And I hate this picture because it's a class diagram, not an object diagram. Don't do that. That's a class diagram. It's a class diagram because it's showing you the methods or it's showing you data. In a true object diagram, it's just going to say customer, payment, invoice, receipts. If you do that on your architectural diagram, I'm not going to mark it off. You see that a lot because people just like to skip objects completely and go directly to the class diagram. So maybe one of these days in the future there won't be an object diagram anymore. They'll phase it out in the UML version 2 or whatever. No more object diagram. Data flow models. Functional transformation processing inputs producing outputs. Input processing output. So it refers to as a pipeline or a filter model. That's a Unix term, Unix shell. We have data flow. Data flow has been around since the beginning of Unix, actually. It's the way that people used to model systems, actually. It was one of the first modeling techniques. Variations of the approach are very common when transformations are sequential. We have batch sequential mode. Not really suitable for interactive systems. So what does it look like? There's your data flow model. That might actually look familiar to some people, hopefully. If you've taken multiple classes from me over the term of your degree, I always talk about data flow diagrams, the entity relationship diagram. It's like a parrot over and over again. So that should hopefully start looking familiar to you. This is an invoice processing system. It's a data flow. That is an architectural diagram. That's an architectural model. So was the class model, object model that I showed you in the previous slide. We have invoices. We read the issue invoices, identify payments, make payments, process through sequentially. Not to be called a sequence diagram, however, or a flow diagram. This isn't really a flow chart, and this is not a sequence diagram in the UML sense of the sequence diagram. So. Now for the hard part, domain-specific architectures. So they're specific to some sort of application domain. Here's a classic example, Android. So you're building an Android phone application. You're going to have a different model than you're going to have in a client server or in another model. You're going to have the phone. You're going to have the different components, the event-driven for the notification features of the phone. I'm not going to get into it because some of you haven't taken that class. But you have different features of the operating environment for which that app is going to communicate with and work with. You model it out completely differently. It's specific towards the Android. iPhone apps are going to have a different architectural design as well. They're specifically designed towards a different platform, different architecture. And I shouldn't say the word platform. It's not necessarily platform dependent. It's architecture dependent. Things that run on tablets are slightly different than things that run on phones, that run on personal computers. Air temperature controller is a totally different architecture to it as well. So think about the domain of the application that you're building, how it's operating, where it's running, and then this is the set of models that's associated with that. Because you can't really use, you could use an object model, I guess. You could use a data flow model, but you can't really show the true architecture. So hopefully you're trying to maybe starting to get the picture about what is meant by the architecture. It's the environment, it's the system, the subsystems. It's, if you could actually physically see what it looked like, that's what it would look like. You have an Android phone and you have all of the different interfaces in the hierarchy of the model in terms of the layering. Two types of domain-specific models. We have the generic model and then we have the reference models. The generic models are abstractions from a number of real systems for which you have encapsulated the principal characteristics of the systems. That would be phone, app, library, you have all the little pieces there. Or you have reference models, which are more abstract, idealized models. They provide a means of information about the class of the system, comparing different architectures together. Generic models are usually bottom-up models. Reference models are top-down models. Bottom-up on the generic, because we're really just interested in the app and where is the app running. And you start from the app level and you work your way up. So in terms of the generic model, compiler models is a well-known example. Here, in fact, if anyone has ever taken a compile design course, I'm dying to teach that course here. I don't know if anyone would sign up for it, though. Build your own compiler. In fact, I've taught it before with Java. You can make a compiler in Java. But to talk about a compiler, we can abstractly break it out generically into different compilation stages, where we have the Lexile analyzer that works with a symbol table. Syntax analyzer, then we can create some abstract syntax trees out of that, and we can perform some semantic analysis on that to figure out what those tokens actually mean. And then we can finally generate some code. That is actually a generic compiler model. And that's, textually displayed. Put it out with boxes. In fact, you take a compiler design course, day number 1, chapter number 1 of the book, you see the boxes. This leads into this stage, which leads into this stage. And look at that, we have source code. Look at that, we have code generator. We have machine language. So generic compiler model can be organized according to different architectural models. Symbol table that's used throughout the entire compilation process, from Lexile analysis to semantic and syntax analysis to code generation. If you're not familiar with a compiler, you really don't need to know anything about it, outside of the fact that the symbol table keeps track of the definitions of all of the different tokens that have been found in the compilation, right from the Lexile analysis, right from the beginning all the way through the code generation stage. So this model is showing you how the symbol table works with each one of these stages, and how the process actually kind of works together, and how Lexile analysis leads to syntactic analysis and syntax, semantics, as it goes through. Language processing system. Here we have one with a repository in the middle, and then we have code generator, optimizer. Again, this is all compilation related stages. Sometimes actually the stages happen inside of the language system if you're in an interpreted environment versus a compiled environment. You could model out the JVM. Actually, if you go online and look up JVM, you'll see the layered architecture of that. You'll see the security system with all of the different subcomponents that are part of the Java virtual machine. But this is language processing as an example. Reference architectures. So these reference models are derived from the study of the application domain rather than the existing system. So it may be used as a basis for system implementation or to compare different systems. And it acts as a standard against which systems can be evaluated. So it's a reference model referencing the domain that the application may or may not work with, depending upon how you're doing the model. OSI model is a layered model for the communication system. So the OSI would be, actually, sometimes I refer to it as the reference model. I guess you're familiar with the open systems. What does OSI stand for? Open system integration or something? All I remember is all people seem to need data processing. A for application, P for presentation. I'm not going to go through though. Maybe it's in the slide. It is. Here we go. All people seem to need data processing. Hey, I remembered it. Actually, that's how I memorize things. I have to come up with words for it, which makes sense for me. Other people learn in different ways. But this is the reference model for the OSI model. This is an architectural design. You've seen this one before too. If you've taken a networking class and I've introduced to you, actually the DoD model is a shortened version of that. In fact, the DoD, don't quote me on this one, that might actually, no, that's a subsystem of the DoD. I think we got something above it. I can't remember what it is, but it's been a while since I've taken a networking or worked with networking. But anyway, this is a classic example of an architectural model of a reference from the OSI. All right, let's sum this up in a painless way. The software architect is responsible for deriving a structural system model, the control model, and the subsystem decomposition. So that's all you're doing. You're not telling me what is application, you're not telling me anything about. You're just decomposing it and showing me the layers or the structure. The large systems rarely conform to a single architectural model. Yeah, your pump is probably not going to conform to a single. It would be too easy. If I said, give me a architectural model of the OSI model. Here it is. It was too easy. Let's see. System decomposition models include repository models, client-server models, and abstract machine models. So we have got a lot of them that are mixed up inside of different representation. Control models include centralized control and event-driven models as well. Modular decomposition models include data flow and object models. That's why I say the object model is probably the easiest. I don't know. It's great generic. Modular decomposition is very generic in terms of what it's accomplishing. You can decompose any system into smaller subcomponents. And domain-specific architectural models are abstractions over an application domain that are specific to the application domain. In fact, you can actually model, if you're trying to transfer, you have an iPhone app and you're trying to make it into a Google app, you could do an architectural design of the Apple, architectural design of the Google environment, do some compare and contrast between the two, easily see how some of the changes in the application design might actually have to be done. Maybe the system notification is different, or maybe some of the protocols are different or something. So you could use that as a means of understanding the differences. There may be construed by abstraction, maybe from an existing system. Maybe idealized reference models. In fact, that's the interesting thing about this OSI model. Everybody knows about the OSI model, but half the people don't understand why it even exists in terms of the reference model. And then they start going, a data link layer, the physical layer, those are the network cards, those are the drivers, where's TCP/IP? They figure out how all the protocols fit into the model. And then you realize, it's just a layer of, it's just abstraction. The whole thing is just an abstract concept in terms of how you're going to organize the protocols and how you're going to build the interfaces to be compatible and follow the standard correctly. All right, that is all about system architectural design. So now you should be able to do assignment number 4, hopefully, and number 5, hopefully, the testing stuff. So next week we're going to have reuse, which is lecture number 11. It's not really about architectural design, which is why I wanted to do 12A first. This is it on the architectural design. Reusable software components is a nice topic to cover. I went through some of the other topics from the lectures I said were optional, and I decided that reusable components was probably the most interesting thing. So that's why I picked that one. If we have any questions, comments, concerns, I can entertain them. Anybody have anything right now? Or you can come up afterwards. So remember, if you came in late, next week is final exam review. Everything you ever wanted to know about the final exam. For those of you people who aren't going to show up, it's multiple choice. Probably about 25 questions taken out of a pool of about 200 to 250 questions. No diagramming for this class. I'm thinking, what else would we have for this class? That's about it. You might end up with an exam that has more questions in one subject versus another subject. It depends upon how there's going to be different versions of the exam. I'm going to hopefully randomly go through and check to make sure that they're evenly spread out. But next week I will have a list of topics that you can be rest assured you will be asked questions on those topics, and I'll tell you what you don't have to know as well, which will narrow things down. Okay. So see you next week.